are really just exponents. So that's what I always tell my students when I teach Algebra 2. I say, remember, a logarithm is just an exponent. We have sort of crafted the logarithm as a way to undo exponents because it's the inverse to an exponent. The logs themselves are kind of man-made structures, okay, for math. And what we really want to take away from logs is that the answer to the log is just an exponent. That's all it is. It's just telling us what exponent. So I have three logarithmic statements. Log base 4 of 16 is equal to 2. Log base 3 of 81 is equal to 4. And log base 9 of 3 is equal to 1/2. On the left side of those statements, you have a log statement. Log statements include a base, that's the subscripted number, and then some other number that you're taking the log of. The answer to the log is the exponent, so on the other side, all of these numbers in this column, these are exponents. So does anybody remember from Algebra 2 how you would write those in exponential form? Oh, Lauren, you want to show us how you were taught to write them in an exponential form on the board?
Yeah.
Anywhere you want. Do you have a method for deciding where the numbers go?
I just remember it goes like left, right, left. Like where there's two numbers, like the smaller one's always like the first number. And then so it's like 4, 2nd, 16. 4 to the 2nd to 16.
Okay, so she thinks left, right, left, back. Maggie?
Like log B, Y, X, that equals X. Like log of B. Like when you write it out, like the 4 would be 16, Y, and
Yes. Okay, so you're like thinking of what like the actual mathematical definition would be. Log base B of Y equals X, and then that would turn into B to the X equals Y. Elise, you say?
The circle thing.
Circle thing. Can you teach us the circle thing?
Yeah.
Some of us may have seen the circle thing before.
So from here to here.
Does that look familiar to anyone? Some people use that. It's just a way, like, you know, Lauren is saying, she remembers left, right, left, and it's like the outside, right, and then the inside. And then Maggie's got her definition memorized, so she knows exactly what's what and where it goes. And then the other way to think about it is always start here because this is your base, right? So it's the base of your log, it's the base to your exponent. Start at the base, go around the equal sign, pick up your exponent. A base raised to the exponent is equal to the thing that you're taking the log of. So you can also use the circle or spiral method to rewrite them. So what would this one say? 3 to the 4th equals 81. And then the last one would say 9 to the 1/2 equals 3. Do all of these statements make sense? 4 squared is equal to 16. 3 to the 4th equals 81. 9 to the 1/2 equals 3. What does that mean? The square root of 9, right? So anytime you have a fraction exponent, the root is in your denominator. So it's saying the square root of 9 is equal to 3, and we agree with that. So what I want you to do at your tables is come up with the answer to this logarithm. Find that exponent for log base 5 of 126. See if you guys can stretch your brain muscles and remember how to evaluate a log. Do we have a confident answer? McKenna, what did you guys say? Okay, so you're thinking about, in order to evaluate a log, I love this, you're thinking about it in exponential form. So you're thinking 5 to what exponent equals 1/25th? And she answers must be -2. Why -2? It's got to change into a fraction, so it was a regular number, it switches into fraction form, that must be a negative exponent, right? And then why 2? 5 squared gives you 25. Okay, so you've got to think about that. If you ever see one where you're going from like a large base to a smaller number, think about roots, right? If this was like base 49 of 7, then you might be taking the square root of 49. Okay, so think about those roots, and then you might have a fraction exponent. Excellent. So here's the mathematical definition of logarithmic functions. Okay. This is very similar to the definition that we wrote down the other day for exponential functions, but now we're switching it up to be logarithmic functions. So the logarithmic function with base a is just written as f of x, or y equals log base a of x. Okay, so that's a basic function. And this little red stuff in quotes, that's just how you say it. So you don't have to tell me log with a little 2 and a big 8. You can just say log base 2 of 8. We all know what you're saying. Okay. But the same things that happened for exponential functions have to be true for logarithmic functions. So the base a has to be greater than 0. Because they're inverses of exponential functions, they're going to have the same kinds of bases. And so we wouldn't have any negative bases for a logarithm. Okay, we'll have only positive bases. And then the base should not be equal to 1. That would be another really boring function. Okay, so that's not logarithmic. And then this is what Maggie was describing, the third bullet point. It's like the definition of how to evaluate or change a log into exponential form. So y equals log base a of x if and only if a to the y equals x. She had a b and an x and a y from algebra 2, but they're the same definition. Do you have a question? Yes. I'll be very careful and never use exclamation. I used an exclamation mark the other day. Reagan, don't laugh at me when I can't talk. It's hard. How would you feel being up here having to talk all morning? Exclamation mark. And another class asked me about that too. Is that factorial? No. We won't use the factorials until chapter 9. Sorry. Okay, here are some properties of logs that you should be aware of. Notice that they are not complete. They have blanks in them. So what I would encourage you to do is jot down the 4 statements that are written so far. And then I'll have you in small groups kind of come up with what you think the answer should be. So could you figure out what the property of log actually is? Now the answer is probably. And then we'll talk about them as a whole and see if we agree to this statement. And we're all okay with the IFS, right? Okay, so when you're working with your small groups to decide what the answers to these are, I would kind of pick one at a time so that you're all kind of looking and focusing on the same one and see if you agree. And what I would encourage you guys to do is once you decide what goes in this blank, think about why that is. So do you have like a justification or a reason that you could give for why that's always going to be the case? So you can go ahead and have a talk with your small groups. Okay, let's come together and share what we've got. What did we say for log base A of 1? It will always be 0. Why? Because A to the 0 is equal to 1. Perfect. That's an easy one. If you're ever taking the log of any base and it's of 1, it has to be 0. That's the only thing that's going to work. What about log base A of A? Just equal to 1 because A to the first equals A. If you have the base and then that value, it has to be 1. Okay, there's nothing else that would work that would be the same thing. Okay? And remember, our base is not 1, so that one's less interesting. I'm going to skip the third one for a second. What do you say for the fourth one? Log base A of x is equal to log base A of y, if and only if x equals y. That's 1 to 1, so that makes sense from what we talked about yesterday, right? If you're taking the log base 5 of 15, the only thing that could equal that in log base 5 would be log base 5 of 15. You put any other number back there and it's going to be a whole new number. Does anybody think they have an answer for either one of these inverse properties, McKenna? It would be equal to x. Okay, think about this. This is in logarithmic form, so we could rewrite it using our circle method. A to the x is equal to A to the x. True? True. So think also about what inverses do mathematically in inverse operation. If you have plus 5, the inverse operation of plus 5 is minus 5, and what do they do? Cancel each other out, right? So if you take log base A of the exponential A to the x, the log and the exponent are going to cancel out. You're just going to have x as your answer. So anybody want to take a guess as to what the second one is going to equal? X. Okay, this one's a little bit harder to do when you're rewriting. Notice that this one is already in exponential form. So if I wanted to rewrite this, I would have to change it into a log. So think about how do you rewrite 3 squared equals 9 as a log. Log base 3 of 9 equals the exponent. So here I'd be saying log base A of x equals the exponent. Log base A of x. True? Yeah. So inverse property is just going to be simply things cancel out. Now, of those properties, you know, 1-to-1 you'll use to solve equations today like you solved yesterday. But of the properties, the two that are most important to me right now are going to be the first two, because you're going to see me use these in my tables when graphing. You know, evaluating logs can sometimes be tricky. So when we're doing a test or a quiz without a calculator, let's pick values that will be easy to evaluate. So I'm going to rely on those first two properties to help me pick my values. Okay. Let's do an example of graphing. We'll start with a basic one. F of x equals log base 2 of x. And this would be in no calculator, so you got to feel comfortable without a calculator. Okay, so I would start with a table of values. And remember, yesterday we did like -1, 0, and 1. The logarithm is the inverse to an exponential function. So remember, in inverses in their graphs, the x becomes y and y becomes x. So those numbers are actually going to pop up on the y side for me. And I'm going to go back and think about these two properties. I'm going to use base A of 1, so I'm going to put 1 in for x. and then base A of A, I'm going to put A in for X. So whatever 1 and A are, those are going to be the two numbers I put first into my table. So on my X's, I'm going to do 1, and then my base is 2, so I'm going to put a 2 there. And those properties should be really easy. Log base 2 of 1 is equal to 0. Log base 2 of 2 is equal to 1. That's the property on the previous slide. So I'm choosing 1 and A, the base. I'll plot those 2 points, 1, 0, 2, 1. And I'm also going to rely a little bit here on my inverse knowledge. In an exponential function, I always had a horizontal asymptote, y equals a number. In a logarithm function, we're doing the inverse of an exponential function, so that y equals becomes x equals. So what kind of asymptotes do I have for logarithms? Vertical asymptotes. So since I don't have any shifting here, it's going to be at x equals 0. This is a basic graph. How do I know it's going to be vertical? Because it's the inverse of the exponential. X becomes y becomes x, so the horizontal became vertical. And also, you can't take logs of negative numbers. If you want to pull out your calculator, you can try log, common log, or natural log of any negative number, and your calculator can tell you you have a domain error. So the domain is restricted in logarithms to only positive numbers. So that helps me draw my graph. I know over here I'm getting closer to my asymptote, and then on this side, it's rising, it's just not rising really fast. So it's not like exponential growth where it just like takes off. This one reminds me a little bit of like a square root function. Kind of grows, but goes slowly. Okay, what's the domain then? All real numbers? No. 0 to infinity. That should also make sense if you think about an exponential function. That was the range of a basic exponential function. This is the inverse, so now it's my domain. What's the range of a log? Negative infinity to infinity. The domain of the exponential function becomes the range of the logarithmic function. Their inverses, x and y switch. X-intercept on this one is listed for me. Okay, so this would be at 1, 0. And then is this graph increasing or decreasing? Increasing. So over its domain from 0 to infinity. Questions about graphing the log? On a side note, just really quickly, I'm going to graph on the same one, y equals 2 to the x. We did that yesterday. Negative 1, 1/2, 0, 1, 1, 2, and I had a horizontal asymptote at y equals 0. So here's my graph. How are those two graphs related? Reflection over the line, y equals x, which is true about all mathematical inverses, right? When you switch x and y, you're a reflection over the line, y equals x. So if I fold on that red line, they map onto each other. Okay, that just kind of reinforces why the horizontal asymptote becomes vertical, why the domain for log does not include negative numbers. Okay, all of that stuff is true. Let's do one with a transformation. Yes, ma'am? Yes. You can do more if you feel, but like evaluating a log, especially without a calculator, sometimes gets a little bit tedious. There's more that you can find, and it's not necessarily hard to find. But we all know what the shape is going to kind of look like. It's going to approach the vertical asymptote on one side, and then on the other side it's going to rise ever so slowly, right? So that's okay. Here's one that is changed, log base 2 of x minus 3. And I'm going to do like I did yesterday, which is, I don't want to overwhelm my sorry, don't want to overwhelm myself with everything that's happening in that function. I'm just going to focus on log base 2 of x, because that will be really easy for me to evaluate. Remember, I'm going to put in the same x's every time, 1 and the base. So this one is base 2. If it were log base 3, I would put in 1 and 3. Okay, so 1 in the base. Log base 2 of 1 is 0. Log base 2 of 2 is 1. Those are going to be really easy for me to evaluate. They're just my properties of log. And then when I plot those points, I'll plot those points in red, 1, 0, 2, 1. I'd think back to the function and say what kind of transformations are happening to the graph. So this graph is going right 3. So I'm just going to take those 2 points and move them right 3. What else will shift right 3 on my graph? The vertical asymptote now moves, instead of up and down shifting, that also shifts my VA. So my vertical asymptote is now at x equals 3. And then you've got a graph. Domain is 3 to infinity. Domain is going to change with your vertical asymptote. That's going to be the start for your x. Range will be negative infinity to infinity. On this one, the x-intercept still happens to be a point from my table. I just shifted it left 3, so my x-intercept is at 4, 0. And this is increasing from 3 to infinity with no decrease. The hardest part, I think, on tonight is going to be like finding the actual x-intercepts if they don't show up like as a plotted point. So on my next example, I'm not actually going to graph it all. I just want to show you how you can find the x-intercept. Does anybody have any questions on this one before I leave it? Yes.
Can we just look at like the point that would make the whole thing one?
Yeah, so that would be like doing the shift in your head, right? So you plug in 4, and then you plug in 5 to make it the same as the base. I'm okay with that in the logs, but you might run into some that are harder to evaluate depending on all the transformations, like if there's a +1 and other things. So I'd like you to try doing the paragraph transformation. And if you want to do it your way, do it your way, but think about the paragraph and the transformations and then make sure those two things match up. Okay, so this example, I'm not going to graph it. Okay, so I'm going to actually just get rid of all this stuff. What I want to do on this example is just focus on how would we find the x-intercept. Because what's going to happen is when I put all those transformations, like it's going right 1, it's going up 2, it's being reflected in the x-axis. With all of those things, the 2 points that I pick originally, they don't show up on the x-axis. So how do you find the x-intercepts? How would you find any x-intercept in math? Plug 0 in for y. Okay, 0 equals 2 minus log base 2 of x minus 1. Now you got to solve this with reverse Pascal. What are you going to do first? Okay, you could add the log to the other side. Log base 2 of x minus 1 equals 2. I like that because now it's positive log. What can you do next? Okay, I heard Lauren is giving me the step and then Zach is explaining the step. Now that you have a log all by itself, you can't undo any of this stuff. Like you can't divide by 2, you can't add 1, none of that stuff's gonna work for a log. So it's in log form, change it to exponent form, is what Zach is saying. And then Lauren says basically use her left, right, left method or your circle method. 2 squared equals x minus 1. So that's 4 equals x minus 1, so x equals 5. Sometimes it comes out to a nice number. There are times where it's going to be like a fraction. So like in my exponential work on my homework, I had some that were mixed numbers. So you might have mixed numbers or fractions again. But now I could list my x-intercepts as 5 comma 0. And I have an exact value. The bell will ring shortly. There are some problems on your homework assignment that have natural log, the ln in them. Those are going to be problems where you could use your calculator. So if I were doing that with natural log, I would use my graphing calculator, type into my y equals, and then pick out the place where I can kind of see where my vertical asymptote is, and pick a few points right near the vertical asymptote. There will also be some solving equations. When you're solving equations, use your properties of logs and think about the x-intercept.